I was tempted to talk about sampling because it's the thing that I do for a living, but then there is no learning at all into sampling, and therefore I decided to focus on another research area where we work on a lot in my group, which is a specific application known as single image super resolution. And I think that's an interesting application because most of the methods that are used in that context are based on some form of learning. And so it's a sort of good playground where we can try different type of ideas and see whether they works. And the idea is to, in this context, to see whether we can use, let's say, the framework of dictionary learning to improve on some existing algorithm, or vice versa, to use some of the existing neural network architecture to inspire new ways to design dictionaries for the dictionary learning context. So that's more or less the idea of the talk, which is therefore sort of divided into 3 parts. I will first, let's see, is there a laser here? Yeah, well, it doesn't matter. So I will first, talk a little bit about this application, single image super resolution, and give you an idea of how that problem was attacked originally and how it is solved currently. And then I'll focus on the unimodal case and try to do a super resolution for the unimodal case. And the idea here is that we start from neural network architectures and try to sort of mimic them using ideas in dictionary learning. And as I said before, we hope maybe to find better way to learn dictionaries. In the last part of the talk, I'll focus on the multimodal case, which means that you acquire information of a certain scene using different imaging modalities. And here the approach is actually different. We'll start from ideas in our community, so sparsity, dictionary learning, etc., to model and to dictate the architecture of a neural network. We'll initialize the parameters of that architecture using, again, ideas in dictionary learning. And we'll show that actually this leads to good numerical results. Actually, we end up with state-of-the-art performance in that context. So it's a sort of cross-fertilization in one way in this case, in the other way in the other case. And let's see what happens. Most of the results are empirical, no theorems. After lunch, we really cannot afford more theorems, okay? This is joint work with 2 students of mine, Junjae Wang and Xin Deng, but this is also the result of interactions and collaborations, especially for the multimodal case with Miguel Rodriguez and the former students of his, Pingfang Song. Right, what is the problem we look at? It's quite intuitive as a problem. So you're given an image, and you would like to enhance its resolution and quality, so you'd like to get a high-resolution version of that image. And probably upsampled by factor 4 or 8 per direction. So typical approach, you divide the image into blocks, which we call patches. And then, not necessarily, but in many cases, you vectorize that patch. So you get a sort of vector X, and then you try to predict the high-resolution version of that vector. And then you turn it back into your patch and put it in your new image. And then you keep doing this for all patches until you get your super resolved image. And so the question is, how do you learn these let's say, function that map the low-resolution patch to the high-resolution one? And lately, all this is done more and more frequently using learning type of ideas. So what people do, they start with a data set, okay, on natural images, for example. In this context, we focus mostly on natural images. So you have a data set with many natural images. Then you artificially create the equivalent data set with the low-resolution images. So you sort of artificially create a set of low-resolution images here. And then you extract patches. So you have high-resolution patches and low-resolution patches. And so they are paired. And then by looking at these pairs, you then try to learn this mapping. And then once you learn, in some ways, a function that from this patch goes to the high-resolution patch, then when you're given a test image, you take a low-resolution patch, apply this function, and that will give you the high-resolution version of that. Now, up to a few years ago, this type of learning was done using dictionary learning ideas. So it was really within our community, I would say. And so essentially, the basic modeling assumption was sparsity. And so the idea is that if you have a patch X here, you can always model it as a linear combination of a small number of elementary atoms, which will be the column of a certain matrix D, which is the dictionary and is a fat matrix. So you really obtain X by multiplying D with a long vector Z, which is a sparse vector. So that was the modeling assumption, which is then used for image super resolution. In the super resolution case, the assumption is that if I have 2 patches, okay, related to the same image, so the low resolution and the high resolution version, They both admit a sparse representation in their proper dictionaries. So I have two different dictionaries, a dictionary related to the low resolution and a dictionary related to the high resolution patches. But then the idea is that the two patches share the same sparse vector. Okay, so that's the modeling assumption that was used. And therefore, the idea is that if I have access to this guy and if I have both dictionaries, I first, given the low resolution patch, find the sparse vector related to that patch. And then I couple it with the high resolution dictionary because they are the same. And then that gives me the high resolution patch. Okay, that was the idea here. And so the question is, how do you do learning of these two dictionaries? Okay, and then the low resolution dictionary is learned using standard methods in dictionary learning. For example, the KSVD algorithm. So what you do is you have many patches, okay, which are here. You stack them together. They give you this big matrix. And then essentially you try to model it as the product of two matrices. One would be your dictionary, okay, your, let's say, low resolution dictionary. And the other would be these long vectors, and the constraint is that they are sparse. Okay, and in all this factorization method, you iterate between the two. So you assume you have D, and then you find Z, typically using some of these greedy algorithms for finding sparsity, like orthogonal matching pursuit. Given Z, then you update D. And there are various ways to do that. A popular approach is known as KSVD. Okay, so by doing this, you learn all the sparse vectors related to your low resolution patches and the dictionary related to the low resolution patches. Okay? Then the dictionary related to the high resolution patch is actually learned directly. So you take this matrix that you have learned, you replace this with the high resolution corresponding patches, and then you just have these two matrices, you find this other one here. Okay, so there is sort of not learning for the high resolution one, is sort of learned directly. And that's a way to sort of couple the two dictionaries. Okay, so once this is done, so you have your two dictionaries. The algorithm, given now a new test image, which is not in your training set, is a new image. You extract a patch. Okay, given your dictionary DLR, you find the sparse vector. And again, you maybe run, let's say, orthogonal matching pursuit on each patch to find the sparse vector. And then you multiply the sparse vector by the high resolution dictionary, and that gives you the high resolution patch. Okay, these are some numerical results, and things were working pretty well. This idea was originally introduced by Young, and then was refined by Elad and co-authors. And then in 2014, Timofte came up with a fast version of this idea. It's an algorithm known as A+, which was very popular up to a few years ago. Okay, so what can we say about all this? Okay, so there is a modeling assumption, which is sparsity. Okay, there is a little drawback here, which is normally hidden under the carpet, and that the problem is that this algorithm is still complex. Okay, because you need to run OMP on each patch. Okay, and okay, there are fast methods, whatever. But normally, when you do learning, the expectation is that all the complexities move into the training, and then when you actually have a new image, things are fast. Okay, and here things are not that fast because you still have to do something relatively complex. Okay, if the image is pretty big, then okay, it's not the end of the world, but it's actually not that fast. Okay, so this is where we were up to 4 years ago, maybe, and then deep neural network arrived. Okay, and they sort of took over the topic. Okay, gradually but surely, and I think now most of the successful algorithm on this problem, let's say if you measure performance even in PSNR, which is what we tend to like, are based on a neural network. Okay, so how is the neural network working? Okay, so here I have, let's say, some notation which is very similar to what Remy did yesterday, so I'm pretty happy with that. But what the neural network do, you take the low resolution patch as input, okay, and then you sort of linear combine your pixels in the input here, and you can model this with a matrix W1. Can be an unstructured matrix, or if you are having a convolutional neural network, the matrix will be structured, but you can still model it as a matrix. Then you add a bias, and then you have a nonlinearity, which is typically the real operator. Okay? So what's happening when I'm moving gradually in this direction? I am gradually going from the pixel domain into the feature domain. Okay? So in some sense, I am gradually trying to get that sparse vector, at least if we still accept this sparsity type of model, I'm gradually trying to get that vector Z that before was obtained using orthogonal matching pursuit. Okay? One layer is not enough, so you do it several times. You have maybe a second layer. You are adding some redundancy, so this matrix is a little bit bigger. you have the bias term, and then you have a nonlinearity, and then you keep doing that a few times. And then the last layer, as Remy highlighted yesterday, is a pure linear layer, especially if you have a regression task, like in this case, you need to reconstruct something in the image domain. So essentially, you have obtained here your feature vector, and then you combine the entries of that feature vector using this matrix, and that should give you the high-resolution patch. Okay? This is a basic architecture, but essentially the most successful architecture used for this problem more or less work like that. Okay? Okay, so our goal now is, okay, we observe that, okay, we have a matrix here, could be a dictionary, all right? And then if I combine the bias with the ReLU, especially if I have a regression task, I can actually replace it with a soft threshold operator, which is what we would like to do, okay? And then if I think of that, then each of these layers is very similar to something related to our dictionary learning problem. And so the goal here is to try and see whether we can use the machinery of dictionary learning to sort of, let's say, learn these matrices in some sense independently, but also in a sort of more controlled way, and to try and see whether we can gain some insight of what actually the neural network is really doing. Okay, so that's the first goal of the talk. And before I go ahead, let me use, let's say, repeat some common jargon which is used in the dictionary learning literature for those who are not that familiar with that. So far we've looked at this type of dictionary, which is a fat matrix, and is normally known as the synthesis dictionary. And the model is that you have a patch, as I said before, and you think that you can model the patch as the linear combination of a small number of columns here, which are elementary atoms. Okay? And this vector is sparse. Then you have what we call the analysis dictionary, where instead you have a tall matrix rather than a fat matrix, and you're trying to achieve the dual. So you start with your patch, and you're trying to get the sparse vector in some sense. Okay, so here your elementary atoms are along the columns here. Okay, so if I go back to this architecture here, and I try to model it using dictionary learning, let's say, jargon, then I end up with an architecture that looks like this. Okay, if I assume I have 3 layers, then I have a sequence of 3 analysis dictionaries. Okay, so I have my input a patch here, then I have a first analysis dictionary, and that would give me normally a first, let's say, feature vector. Then I have a nonlinearity, which is the soft threshold. Then I have another analysis dictionary, another nonlinearity, a further analysis dictionary. I could keep going, but we stop at 3 because otherwise it's really too complex for us to handle that. Okay, and then when you want to resynthesize everything, you have this fat matrix, which is actually a synthesis dictionary. Okay, and the hope, as I said before, is now to get the high resolution version of this guy here. Okay. Okay, and so what we want to do is to try and learn this analysis dictionary sort of independently and try to see whether we can do as well as a neural network. Let me make one simple observation here. Remember that when we do training, we have many of such x's. Okay, so each x is a patch of your image. You have many images. Okay, so imagine that this has dimension d, so it's a vector in a space of dimension d. When you have many of these guys, you have a cloud of these vectors in a space of dimension d at most. Okay? Now, when you multiply this guy by your matrix here, this vector here is bigger, okay, as dimension n, whatever it is. Okay, so it lies in a space of dimension m, which is larger than d, and you have a cloud of such elements. However, the matrix is not expanding the space, so actually this cloud is going to lie in a subspace of dimension d within this bigger space, but they still are in the same, dimension, okay? And then if you don't do any nonlinearity, you multiply by this other matrix, you get something even bigger, and then something even bigger here. So you have a set of huge vectors, but they still are in a space of dimension d, okay? So the nonlinearity may have many rules, but one of the rules which is fundamental is really to sort of help you spreading these clouds of points. Okay? Because without the nonlinearity, it's not clear why we should have all these matrices if you think of it, because more or less, the equivalent rank is the same, right? However, when you had some of this nonlinearity, then you actually change the locations of some of these elements in the cloud, and you're spreading them, right? And so one of the goals, I think, we think, is to try and to couple the design of the nonlinearity with the design of the analysis dictionary in a way that at each iteration you are spreading these clouds of patches as much as possible, because by spreading them into a higher dimensional space, okay, you're sort of disentangling information, and then it becomes easier to map them back to a higher resolution version of the original patch. Okay, and so that's sort of our guiding principles, okay, when we try to do the design of these dictionaries, is to, because now we have a cascade of dictionaries, is to try and couple these two elements in a way that we spread features as much as possible. So the first thing we did is we trained these using, let's say, neural network strategies. You can think of this as a neural network. So you do backpropagation, etc., and we analyze a little bit what we obtain in that case. And there is one first interesting observation that we made. So if we look at the thresholds that are learned using essentially backpropagation, you can see this sort of bimodal behavior. So there is a group of thresholds which are extremely low, okay, and then the other are large and become larger and larger and larger. Okay, so there are some atoms which are essentially always preserved when you move across your network, and there are some atoms which are only preserved in some specific cases. Okay, so if in fact, if you look at the percentage of time that you preserve some atoms over the entire training data set, you can see this bimodal behavior. So there is a group which is essentially always preserved. So goes from, let's say, the input all the way to the output, and then there are others which are preserved only in some circumstances. Okay, so why is that happening? Well, we have our way of thinking of that. So to analyze this, we consider one layer of our system. So you have one analysis dictionary and the corresponding synthesis one. So what happens in this case, you have your patch X, you compute inner products with the rows of your analysis dictionary, and then if the inner product is large enough, it is preserved and then goes into the reconstruction. Okay, so let's imagine for a second that this guy has dimension 2. So all these x's lie on a plane. Okay, so what is visually happening here? So all your x's, so all your patches are on this plane. So you take a patch, let's assume it's somewhere here. You take the inner product with the first atom, and then if it is larger than the threshold, which is this guy here, it is preserved, otherwise it is set to 0. Okay, it's a soft threshold, so it's symmetric. Okay, so you have these two lines, and you are effectively partitioning the plane into 3 regions, okay, based on the threshold. But then you do the same thing with the second atom, which is this guy here. Okay, and therefore, if the inner product is large enough, you keep it. If it is below the threshold, which is this guy here, then it is set to 0. Okay? So based on that, you're essentially gradually partitioning the plane. Imagine that you have a cloud of patches here, and you are gradually partitioning the plane according to how you decide this direction, right, and how big is this threshold. Okay? And so the expectation is that you are partitioning the plane, and then your partition should follow the properties of your data. So if your data has a certain manifold type of structure, like the one shown here, you expect that these directions and the corresponding thresholds are such that they will create some regions which sort of follow this manifold. Okay? And that's definitely one of the things that we expect the neural network to do. And we think that this is done by the atoms here, where you have a fairly large threshold. Okay? So this is what gives you some form of selectivity. And they are designed in a way that if you have something, a very peculiar shape in the manifold, when you have something very peculiar, you create a specific inner product that will preserve that set of elements if they are very aligned with your inner product. Okay? But the second observation is that obviously you have a threshold, and so you are creating this black region here, and everything which is inside the black region will go to 0. So it's lost information. Okay? And so there is a danger that if this is not designed properly, then you may lose some information which is relevant. So what you also want to have is some atoms that are just focusing on preserving, in some sense, a common information that you would always see in your patches. And we think that the atoms related to the threshold, which are very low thresholds, actually are only targeted to preserve that information, so to make sure that the information goes from one layer to the other. So based on this type of intuition, then we try to design our analysis dictionary by splitting them into 2 parts. So one is related to preserving the information, and so should be mapped with a very low threshold. And then another which should focus a bit more on let's say, the shape of this manifold, so it should be related a little bit more to some form of clustering, where you try to cluster a group of patches which have some peculiar characteristic together, and then you try to represent that using a specific atom. And then that should be related to a much higher threshold, because obviously you want to keep that atom only if you have a patch which is very close to that one here. So if you think of the structure, so you have this double structure, then you have a threshold, and so what you expect to see is a vector which is relatively not sparse for the first part and very sparse in the second part. We have a cool name for the first dictionary, it's an iPad. All right, a less interesting name for the second one is just CAD. Okay, so that's really the basic idea here. I'm just going to go sort of quickly on how we learn these dictionaries. The first one, so the one that preserves information, is learned in a pretty standard way. There are some variations, but so I'm going to go sort of quick here. There are some variations, but it's a standard approach. It's a method known as goal, and the reference is here. Give me 1 second. Okay, was proposed in 2013, and is essentially a method where your cost function has various terms which try to achieve a certain goal. One term is related to keeping some sparsity in the vectors that you obtain. Another term is to try and avoid that you further collapse your space. Okay, so if your row atom were all the same, right, then the result would be that the resulting vector would lie in a very low dimensional space. And then there is a further term that tries to make the rows of your dictionary as different as possible. Okay, the only variation we have here is a term here, W, which is important because we do this layer by layer. So it's not that important at the first layer, but then for the other layers it becomes more important. And this is really to enforce as much as possible the fact that given a cloud with a certain size, which lies on a certain subspace, you don't want this subspace to shrink. But besides that is a standard approach. And then we have a small threshold here, which we set essentially inversely proportional to the variance of the coefficients of the feature vector. For the other dictionaries, so we need to perform some form of clustering, okay? And then we need to couple that with the right atom and with the right threshold, okay? So here we need to impose a model. Okay, we impose a model on which we can have some control. It's not necessarily the best model, especially for images, but we assume that all our patches can be described using a mixture of Gaussians. And then essentially what you want to do is, and I'm going to show that sort of graphically, assuming you have this set of Gaussians, you want to have an atom that describes pretty well all the patches which are in one of these Gaussians. Okay? So we first need to learn this mixture of Gaussians, and then once we've done that, we can try and learn the various atoms. Now the idea here, and it's sort of shown here graphically, is that when you try to learn this mixture of Gaussians, especially for patches in images, you'll have that most of the clouds of these patches is centered around the origin. Okay? So you're always going to have a sort of Gaussian that will look like this, and then you have a few, let's say, outliers here and there that you'll need some new Gaussians to describe. Now the intuition is that this guy here is the guy that we are actually taking care of with the iPad dictionary, so we don't care about this. So what we want to create are some new atoms that are really focused on maximizing the information related to this, the preservation information related to these peculiar, let's say, atoms. So the way we find this atom here is essentially by finding a direction such that the average inner product between this atom and all the patches which lies with this simple model is minimized, whereas the average set of inner products between all the patches here with this guy is maximized. Okay, so that's our optimization criterion. And then we set a threshold that essentially further maximizes this separation, so makes sure that these peculiar guys are preserved, and everything else which is actually overlapping with the previous guy is removed. Okay, and then we have the other Gaussian model, and then we learn another atom this way. Okay, so that's essentially the way we find an atom, which does exactly what I said before. We try to maximize the inner product with the patches which are within that peculiar Gaussians, and minimize the inner product with the patches with the not that peculiar Gaussian. This is the distributions of the inner products, and then we pick a threshold which sort of separate these distributions as much as possible. Okay, so let me show you some visual results. Okay, let me probably jump directly to the case of layer 2. So we do this layer by layer. So we first learn the first layer. Maybe let me go back here. So these patches are learned using the standard, let's say, method. And these patches are learned using this mixer of Gaussian model. And then there are corresponding thresholds. And so if I look at the percentage of times that I preserve a certain atom, we have that these guys here are preserved 99% of the time, and the other are preserved only a small number of times. And then after I have these, all the features vector that are here are then used to train the second analysis dictionary. And this is the analysis dictionary that we obtain. This is, again, the part related to preservation of standard information. And these are the atoms that we obtain using this mixer of Gaussian type of approach. If I then combine the two matrices, I get the equivalent dictionary, which is shown here. And I think you can notice sort of slightly different behavior. In particular, there is much more structure here, because here you're trying to find something which is sort of peculiar, whereas these other guys are either very smooth or sort of, centered around the origin. Okay, the second point I want to make is this idea of spreading, okay, the features as much as possible. Because that was one of the goals. So this is shown here. So what we do is we look at this cloud of patches after the first layer. Then we do an SVD to have an idea of what is the subspace that they are covering. And so this is the distributions of the singular values. Okay, so that gives you an idea that, okay, this is more or less the dimension of the subspace that they are covering. When we then apply the second dictionary and the nonlinearity, then you can see that we have spread a lot this set of patches. And I think this is going to help the performance. Oops, okay. The synthesis dictionary is learned in a pretty standard way, so we can skip that. Okay, so let's try and see what happens in practice. So what is interesting is that, okay, this approach beats the shallow original approach for super resolution, but also here is the dictionary deep model that we have discussed with 3 layers. And then we actually just learn a neural network with the same architecture. So it's not very difficult, not very complex architecture, okay, because we cannot go beyond that. And you can see that actual numerical performance are more or less equivalent. So that means that this type of design has led to something. It's interesting to observe that this uses ReLU as a nonlinearity, and this is using the soft threshold as nonlinearity. And for regression tasks, the soft threshold, it's definitely not worse than the ReLU case. Okay, so let me move on to the multimodal case, where we're trying to do the other way around, as I said before. Now we're trying to use dictionary learning to design a neural network rather than the other way around. So first of all, what is the problem? So the problem is that you may acquire the images of a certain scene in different modalities. Maybe the most a canonical example is given by the case where you have a visual image, color image, and a depth image. Okay? And the problem is that these acquisition devices have different resolutions. Typically, the color image or the visual image has a higher resolution than the other modality. And so we still want to do super resolution, in this case on the depth image. But besides using the low resolution version of depth, we also want to use the high resolution color image as side information. Okay, this is a quite interesting problem that happens in many contexts. And actually, we are faced with a similar type of problem in this context in art investigation. I added these slides yesterday evening after seeing the talk of Carola. So Carola is doing some work on art investigation. Hi, Carola. We are also working on imaging for art investigation. I'm talking to the camera because Carola is watching us somewhere, and we also do that. Okay, we are very good. But so this is a joint project with Miguel Rodriguez, who's actually leading it, and the National Gallery. So what happened in that context is that you have a visual image of a paintings, and then you acquire the image using different modalities, for example, X-ray. This, in this case, is what is known as fluorescence X-ray. And again, these other modalities normally at a lower resolution. And so the curator would like to be able to see, let's say, this image at the same resolution as the color image, so that some comparison would be easier. Okay, so that's an instance of this problem. Okay, so we want to combine these two guys to get this guy here. How are we going to do that? The first issue is how are we going to model dependencies across modalities? And here we're going to resort to sparsity type of ideas to model that. And our model has been inspired by a work by Miguel Rodriguez and co-authors. And their idea is the following, is that when I look at the same modalities, we stick with the idea that both the low resolution and the high resolution patch share the same sparse vector. Okay, so we stick with that idea. So imagine this is depth, so they share the same sparse vector. But then you have the color image. Okay, so in that context, you would have, for example, something which is piecewise smooth and texture. And so the intuition is clear that the piecewise smooth, okay, will have features which are almost certainly in common with the depth. Okay, not exactly the same, but more or less in common. However, texture is something that you would normally see only in the image, and therefore this would lead to some sparse elements in your vector which are unique to the color image. So the model essentially is to say the same modality, they share exactly the same sparse vector. Across modalities, subset of these vectors are in common, and subsets are actually unique to each modality. So this type of model leads to a structured type of dictionary, okay, which is shown here. Okay, that's the work of Miguel and co-authors. So you end up with this type of dictionary. So here you have your low resolution depth patch, high resolution depth patch, and this would be the color image, the patch. Okay, so these two guys share the same sparse vector, which is this guy here. Okay, so you have these matrices modeling the dictionaries, and this is in common. Okay, then you have this guy here, and part of this guy has a sparse representation, which is this one here, which is in common with the other two guys, and then has something here which is unique. So the vector V is unique to the color image, and the sparse vector U is unique to the depth images. Okay, so that's the model. So we consider a minor variation of this model in our approach, which is shown here. And the idea is that, again, the low resolution depth and the color image have some sparse representation in proper dictionaries. Okay, and then this sparse representation contributes to the sparse representation of the high resolution depth image, and this contribution is found through a linear mapping. So we have two matrices here and then a soft threshold here, and that will give us the sparse coefficients. Okay, so the model is shown here. The low resolution depth has a sparse representation A in a proper dictionary. The high resolution depth has another sparse representation B. This is the color image. The high resolution depth has a third sparse representation C. A, B, and C are related through this type of model here. So you multiply A by a matrix, B by another matrix, and then you have a soft threshold. So that's the model we have. So given all this model, we need to learn all the parameters of the model. So the three dictionaries, dx, dy, dz, the two linear mapping here, wx and wy, and then obviously the corresponding sparse vectors, which we don't have. Okay? We learn all these in a standard, let's say, dictionary learning way. So essentially, you iterate among all the parameters, you fix a subset, and you learn something, and then you fix another subset, and so on and so forth. Okay? And you iterate several times. Once you've done that, if you were to do standard dictionary learning, then we would be back to what Elad was doing before. So we would be given the low resolution depth and the high resolution image patch, and then we have to find the sparse representation A and B first. Okay, so that would be the problem, and then you would run a standard algorithm like, as I said, orthogonal matching pursuit, or you can run an iterative shrinkage type of method, which is described here. So you have a first estimate of your sparse vector, and then you do a gradient sort of update. You have a threshold, and that gives you the new version, and then you iterate. So you can model this with this block diagram here. So you have your AK minus 1. This is the low resolution patch, and through this block you get AK, and then you would go back here, and then you iterate the process. Okay. So a few years back, there was this idea of unrolling these iterations. Okay, is a paper known as Lista due to Jan LeCun and co-authors. And so the idea is that rather than going back here, okay, let's think of this as one layer of a neural network. So this AK then becomes the input to a next layer. Okay, and the structure of the layer is the same as this one here. So it is sort of shown here. So you have, this is the block that I showed you before, and then rather than going back here, you actually have another layer which look like this one here, and that will give you AK plus 1, and then you have a few more layers, and so on and so forth. And so you are sort of unfolding this iteration. Okay? Now, what is the advantage in some sense of doing that is that now, for each layer, you don't need to have always the same parameters, so the same dictionaries. So all of a sudden, you can have a dictionary D1, D2, and so on and so forth. You don't have to have the same threshold. You can change the soft threshold. And the third thing is that this would normally be the transpose of this dictionary. It would be a tall matrix. You can have a new dictionary P. OK, so if we do this for both modalities, we end up with this architecture here. And then we can merge the two architectures using our model. So the idea is that once we find the two sparse vector, we have our two matrices, then the soft threshold here, and then the synthesis dictionary for the high resolution patch, and that will give us the high resolution version. So that leads to this architecture, which is a deep network architecture, which has been inspired in part by our type of modeling of dependency across these two scales. So if we were Yann LeCun, what Yann LeCun would do, once he has unfolded his iteration, he would just apply backpropagation to learn all these parameters. Okay. Instead, what we're going to do is to say, all right, we actually have learned these sparse vectors here. We have learned all these parameters. So let's start and update them so that we actually end up initializing all these parameters in a way different from what people would do normally. And after that, we can run backpropagation. So that's our idea, is that rather than running backpropagation straight away, why don't we actually try to anticipate the type of parameter that we should see here? Okay. So how can we can do that? Okay, imagine that you are here. Okay, so you know you found this bk minus 1 here. This is the sparse vectors at iteration k minus 1. Okay, so then you know what is your target. This is the sparse vector that, let's say, orthogonal matching pursuit would give you. So based on that, you know G. Okay, you know bk. X is the incoming patch. So you know all these. And so your optimization is on these two matrices and on the soft threshold. Okay, so you have to optimize this soft threshold here, this dictionary, which is a synthesis dictionary, and this one here, which is an analysis dictionary. Okay, so in spirit, this is similar to a typical problem which is known as analysis synthesis dictionary learning. It is in spirit similar, but actually the optimization that you have is slightly different, but one can use some of those ideas to run this optimization. So again, you can optimize by fixing two of these, let's say, 3 parameters and learning the third one. Okay, so the first thing we do, we fix, for example, the threshold here and the synthesis dictionary, and we learn the analysis dictionary. Okay, how do you learn that? You learn it row by row, so 1 atom per time. So if you look at this expression for 1 row, you have to do this minimization. Now, the typical difficulty is that you have a nonlinearity here. But since this is fixed, you're assuming that this has already been found, then what you can do, you can split the entries here according to what the linearity is doing to these entries. So if the nonlinearity is setting these guys to 0, okay, then the entries related to 0 will have only the contribution by this guy. Otherwise, if this quantity is large enough, okay, the soft threshold is preserving that value and just shrinking it by the value lambda. So based on that, what you can do, you can split all the entries in your cost function according to what the nonlinearity is doing. And then based on that, you end up with this equivalent cost function where the nonlinearity has now disappeared because you have included that. So this term, as I said, is related to all the elements here which have been set to 0, and these are the elements which have been preserved by the nonlinearity. This term does not affect the optimization over P, so you can forget about it. And so you have just to optimize, minimize this quantity here. Our cost function is an L2 norm in this context, which is good enough, and so you have a closed form solution for that. So once you find the various atoms of the analysis dictionary, then you do the same for the synthesis, and the synthesis, actually the optimization is essentially the same, so you use exactly the same trick. And then once you learn the synthesis dictionary, you learn the nonlinearity. And the nonlinearity, there are 2 things we do. First of all, it's not the same nonlinearity for all the entries. We have a different nonlinearity per entry. And then you find it through an exhaustive search, which is actually, given it is 1 parameter, is actually relatively fast. And that's, in any case, at the training stage. So in this way, okay, we iterate the process. And in this way, you learn all the parameters of 1 layer. And you do that layer by layer. Okay, so it's a sort of layer-wise optimization. And once we've done all this, so everything has been initialized, then we run backpropagation as in normal neural networks. Okay, so let's look at the results. This first thing I want to show here is the training loss, so the error that you experience when you train your neural network over the training data. Okay, And what is interesting is that the blue line is what you obtain if you use standard initialization. So you have your architecture, you use standard initialization, and then you do training. The green line is what you have if you do the initialization this way, the way that we have introduced. And to observation, obviously, you can see that the green line gives you much lower loss. The other thing is that here we are increasing the complexity, so we're going from 2 layers to 4 layers, and the dictionary size from 256 to 512. The gap remains. But what you can observe is that in some sense, you need to go to 4 layers of 512 in order for the standard initialization to be as good as this initialization. Okay? So that indicates that it's not that true that neural networks are not affected by the initialization. Probably to do that, you really need to have a huge neural network. But also that if you do the right one, okay, then you can use a much simpler, smaller neural network. For the simulation that I'm going to show next to this, we're going to use 4 layers. Okay, so it's actually a relatively small, shallow network, let's say, compared to standard methods. So these are the numerical results, which are actually also very good for those who care about numerical results. So this is a depth image, enhanced using also the color image. So this guy here, that's the ground truth guy. And here you have all existing methods. The worst methods are not based on deep learning. The other are actually based on various forms of deep neural networks, quite sophisticated. And this is the method proposed here, which numerically is actually consistently the most effective one. OK, that's also on another data. I want to conclude by showing you these last slides, which I think is intriguing. So what we did, we looked again at the distribution of the nonlinearity on the 4 layers. Okay, and this first row is by just doing our optimization, so before backpropagation. And this is what happens when, starting with this, we run backpropagation. And again, it's quite interesting. You can see this bimodal behavior. It's not that evident after our initialization, but then when you look at the neural network, you can see how the threshold for a certain set of atoms is very small, and then it becomes suddenly relatively large, obviously increase more, but you can really visually see this bimodal behavior. So that seems to appear, whatever the context you consider. We think that the atom here has become more selective through backpropagation, and therefore you can afford a bigger threshold. So you're sort of, I don't know, spreading and describing the information more efficiently, and therefore the network can afford a bigger threshold. We cannot achieve that by just doing this layer-based optimization. This is how these atoms looks like, and that's my last slide. So it's interesting that the atoms related to this region here are way more localized than the other atoms. And we don't really get this by standard dictionary learning, so there is still something that we don't do as a neural network, which is probably, okay, probably not good news, but we don't know. Okay, I can conclude here, just saying a couple of concluding words. So this work has been about some form of cross-fertilization between neural network and dictionary learning. We've done this one way, as I said before, in the unimodal case. And the core idea there is to exploit this bimodal behavior and to try to couple thresholds with the atoms, which gives some good results, but numerically is not beating state of the art. In the multimodal case, we have operated the other way around. So we use our type of modeling to design this architecture. And at least from a numerical point of view, this approach is actually very successful. Thank you very much.